access by typing my name in the Google. So it is regarding hands-on sessions on learning robot kinematics using RoboAnalyzer. The software is developed by Professor S.K. Saha, Department of Mechanical Engineering, IIT Delhi, and his PhD student. Contents are robotics, robotics for education, homogeneous transformation, Dana-Hartenberg parameters, forward kinematics, inverse kinematics, motion planning. So, robotics is the study of robot design, development, control, and applications. There are various applications of robotics like in industries, academics, research, entertainment. We might have seen robot movies, medical applications for surgery, and nowadays it is being included in curriculum of universities. So these are some figures of robots developed by Mechatronics Lab and PAR Lab, IIT Delhi. So generally, robotics is being taught theoretically and practically, like in theory, design and working of robot in the form of drawing and pictures. Mathematically intensive, there are much uh, applications of mathematics in the robotics. You will find very big equations. In practical, we study about the CAD modeling and simulation. We operate the actual robot, real robot. Okay, and not many institutes have facilities where there no actual robots are there, no laboratories are there. In that case, the visualization of software named RoboAnalyzer is very important. The software name is RoboAnalyzer, and it is very good for visualization of kinematics, dynamics of a robot. So, what are the basic concepts of robotics? So, these are homogeneous transformations, DH parameters, kinematics, dynamics, motion planning. Oh, it is very difficult to visualize. Homogeneous transformations, what is this? DH parameters, all these can be visualized. So the RoboAnalyzer software. Okay. So freely you can access by this website address, and the RoboAnalyzer software is a 3D model based robotics learning and teaching software developed by Professor S.K. Saha and his team at IIT Delhi. The main developer is Mr. Raju Lochan G. Chitta Wadigi. Other developers are like Dr. Suril Saha. He is presently working with IIT Jodhpur and many more. So this software can be easily downloaded, and after download, just unzip it. Okay. Okay. Now coming to the software. Okay, so one can easily get it by typing Rover Analyzer in the Google, then you will find it. See the left side, there is a downloads. After after this page, you will find the number of versions. The recent version is Rover Analyzer V7.5. And what is the new feature added in this version? Homogeneous transformation matrix, which is known as HTM module. So by clicking this, one can download it, and already I have downloaded it, which I'm going to access. Yeah, this one. So before the actual software, Rover, why not to get exposure of HTM module? Okay, see, there are two coordinate systems. Both are initially coinciding to each other, the bigger one and the smaller one. These are also known as frames. Okay. Now, if you see the top panel in this window, HTML module, so there the things, file, transformations, sequences, view. So the present view is isometric view. Also, we can visualize X, Y plane, the coordinates in the XY planes, YZ, XZ. Okay, coming back to the by default isometric view. Okay, if you see the right side in this module, so see there are two things, local transformations and the global transformations. Local transformation means suppose we are going to measure the positions of the end effectors with respect to the base frame, means the frame, the coordinate system attached at the robot base, and we are going to measure the end effector position, that is the local transformations. Okay, and the global transformation, suppose there is a some coordinate system not at the origin of the robot, and with respect to that, suppose we want to measure the end effector positions and the orientations, then it will be known as the global transformations. Okay, now transformations can be classified into three categories: pure translation, pure rotation, and a combination of both translation plus rotation. Okay, and one thing is observable here. See the matrix, okay, and see the last column, which denotes the position vector. If you see 0, 0, 0 values, so y0. If you see x, y, z values are 0 here. That's why the last column values of position vectors are also 0. Also, there is no rotation. Both frames are coinciding to each other. So, if you see the rotation matrix 3 by 3 matrix, these 9 elements, okay, which is known as the rotation matrix. Okay, and this total matrix is known as homogeneous transformation matrix. Why it is known as homogeneous? If the number of elements in the rows are matching with the number of elements in the column of the other matrix, then it is known as the homogeneous matrix, and then only we can multiply 2, 3 matrices depending upon the transformations, and ultimately we can get the kinematic equations, means robot and effector positions and the orientations. So this transformation matrix gives information about both the orientations and positions of the robot. Okay, now just have a feeling like if we put x is equal to 5, then what is happening? If I'm clicking this translate, okay, see, so it got moved along the x-axis. Okay, now resetting it, same I'm doing for y, c, okay. Why this is? I wanted to move it along the y direction, but I forgot to put x is equal to 0. So, which I'm going to do again here, I put x is equal to 0, y is equal to 5, and c. Resetting it, putting y is equal to 0, and z is equal to random values like 7 I'm putting here. Okay, c. Okay. Similarly, we can also have exposure of rotational transformations like a rotation about x-axis. I'm putting value of 45 degree and see the rotation. Yeah, see, rotation is about x-axis. So both the axes are collinear, but other axis got rotated by the same angle, 45 degree. If I do for rotation about y-axis, then see the y-axis will not move. They will remain at the same axis. Okay, this is y, and this green color is for so this is the x. The green color is for y-axis. Okay, now see what's happening. See, this can be visualized by zooming out. Okay, similarly, if I put rotation about z, so see z-axis of both the coordinates are on the same axis. There is no uh, rotation. Okay, means both are at the same place. And see what are the things happening. If you see this transformation matrix, so these values got changed. The values of rotation matrix got changed. Means it is not a unit matrix. Okay, means there is some rotation. And if you observe the last column, still the position vectors are 0, 0, 0. Okay, so can we change it? And after putting z is equal to 7, then what is happening? See, and see the position vector for z direction got changed. This 7 z is equal to 7 is updated here in the matrix. Okay, and if you see the below this one, so all the transformations are multiplied in the sequence. Okay, like Now y is equal to 4 I'm putting here. Okay. So see T3 is added in the this sequence. Okay. And suppose now I'm doing a rotation about x. Okay. So see R4 is added in this sequence of multiplication. Okay. So can we visualize these all things? Animate. So can we do it? Yeah, by clicking the sequence, what the sequence we have followed, and R4 the sequences it is taking. Okay, coming back to the main software, the Robo Analyzer. Okay, by default, this robot is coming into the picture, and the DH parameter you can see on the below panel. Okay, see default robots, which kind of robots, 2 degree of freedom robot. And what about the joints information? 2R, revolute joints. Okay, and suppose we want to visualize two prismatic joints. See, it becomes like this. Okay, and we want to move the coordinates. See what is happening, and it is taking values of these ds parameters. Joint number 1 values it is taking. Now it is taking joint number 2. Joint angle is here minus 90. Link length is 0.15. That's why it is going down. Okay. In this way we can visualize the motion of the robot. Okay. This also we can change, like suppose we want to visualize 5 degree of freedom robot. So what we are getting here, this we are getting. Okay. And there are two ways for the validation. One by the movement of this robot, and other by the graphical representation. Okay. In this way. So right now we are dealing with the 3D model. So now forward kinematics, you know forward kinematics already, and we want to play this motion. See what is happening. Okay, and this path is known as the trajectory. It is given to the robot to follow the specified path. Okay. Now we want to visualize it through the graph. Okay. And we want to know about where is our end effector. So and effector in x direction, y direction, z direction. Okay. If you want to visualize joint values, so in this way we can visualize. Okay. What about if you click force or talk? Okay. So what is saying? Simulation data that doesn't exist. Okay. because we are dealing only kinematics. Okay. Now coming to the 3D model. Okay. In this way, we can visualize the motion of a robot. And now I'm clicking this inverse kinematics. Okay. So after clicking this, it is getting updated, and the values are now updated here. So inverse kinematics, the end positions will remain same. Means for the given in all solutions, there are 8 solutions displayed in this panel. So and effector positions x is equal to 0.35 meter, y is equal to zero point 0.1, like that. So the and effector positions are fixed. But depending upon the other inputs like a joint offset, link length, twist angle, the joint variables are being changed. Okay, means we are getting multiple solutions to reach the same goal point. Now, suppose we want to visualize the solution 8, means the joint variables are these are. Okay, now after clicking, so okay, so what is happening here? Okay, see, and what about, suppose I want to get solution 5. At this stage, we don't know which one solution is the best one. To know that, we need to apply optimization techniques. Here, randomly, I am clicking to know the configuration. Like solution 5, see, configuration change हो गया है इसमें. Similarly, solution 1, solution 4. But one thing to remember, and effector positions are at the same point. Okay, but the joint variables are changing, and due to that configurations, we are getting different configurations. Okay, now inverse dynamics. Okay, for that we need to do firstly forward kinematics and then inverse kinematics, and we want to visualize the motion. So to know about dynamics, means forces, what are the forces or torques required to move the manipulator. So we need to take help of graph here. By this we cannot know that how much torques are required. So with the help of this graph we can know. Earlier, if you remember, if when I clicked this force and the torque, so it was saying it doesn't exist. But now I'm clicking and it is showing some values. The curve, we are getting information of the dynamics, forces or torques. Okay, so robo analyzer is the visualization for mainly kinematics, but also we can get visualization of dynamics. Okay, so coming back to the software, yeah, 3D model, sorry. Okay, so in this way we can visualize the motions of any kind of robots. Also we can take data It is not necessarily that whatever the uh, default robots also we can visualize. We can visualize our own made robots. Okay, so and what about jogging? Suppose we want to uh, see the motion of coordinate systems. So this by clicking this base frame to end effector, we can visualize. Okay. Now, yeah, I clicked this virtual robots. Okay. So suppose we want to control joint individually and want to see the motion like joint 1 I'm moving, joint 2, joint 3, joint 4. Sometimes it is very difficult to identify which one is joint 1, joint 2, and joint C6. Okay, okay, in this way. Also, Cartesian control. We can control the hand effectors. Yeah, see what is happening. Here I am controlling the hand effectors. In joint control, I was controlling joints. Okay, here in Cartesian control, I am controlling the coordinates, means hand effector positions, and all these sequence we can record and play like animation. So with this, thank you.